Hello, everyone. Welcome to today's live broadcast, Improving LC Methods for Alberta, the Special Projects Director for LCGC, and I'll be your moderator for today's event. We are pleased to bring you this webcast presented by LCGC and sponsored by Advanced Materials Technology. I would now like to share a quick statement from our sponsor. Advanced Materials Technology is an innovative HPLC column manufacturer focused on improving the presentation of the sample to the detector. Using novel fused core particle design, AMT has challenged conventional wisdom and engineered innovative solutions for the separations community. AMT continues to be a leader in novel, superficially porous particle development, enabling high efficiency and reliability for scientists running both small and large molecule separations, in addition to delivering application-specific solutions designed to meet industry challenges. All right, we just have a few important announcements before we begin. This webcast is designed to be interactive, and we encourage you to ask questions during the event. You can submit your questions by typing them in the Q&A box, which can be found at the bottom of the video player. You can also enlarge the slide window by clicking on the small icon in the bottom right corner of the media player. The slides will advance automatically during the event, and if you have any technical problems viewing or hearing this presentation, please click on the question mark help widget in the top right of your presentation window. All right, I would now like to introduce today's speaker. We're so pleased to be joined today by Dr. Stephanie A. Schuster. Dr. Schuster earned her PhD under the guidance of Professor Joe P. Foley at Drexel University. She joined Advanced Materials Technology in June 2009 as a research scientist working with Dr. Jack Kirkland, providing contributions to the commercial development of products designed for peptide and protein separations. Most recently, as part of the technical support team at AMT, Stephanie has been providing customer support in optimizing and troubleshooting their applications. Thank you, Stephanie, so much for joining us today. Please take it away.
Thanks, Bob, for the introduction, and thanks to everyone who's joining us today. I'll start with a brief outline of my presentation. I'll review the allowable changes with USP Chapter 621 and employing SPP column technology for method improvements. Then we'll go into understanding the impact and benefits of using smaller ID analytical columns. From there, we'll talk about case study examples using both isocratic and gradient conditions. And then we'll wrap up with a summary, and there'll be time for Q&A. So in terms of the USP Chapter 621 guidelines for changing those isocratic and gradient methods, the changes went into effect December 1st, 2022 for USP, and then in terms of the harmonization for BP, EP, and JP, those changes went into effect January of this year. Just as a side note, they had allowed changes to isocratic methods as of 2014, but the really breakthrough part of these updated guidance allowances is in particular for gradient methods, which they hadn't allowed changes to in the past. So let me step you through what the allowable changes are. In terms of the stationary phase, you do have to keep the same L category for both isocratic and gradient methods, but the change from totally porous particle to superficially porous particle columns is allowed. In terms of column dimensions, the particle size and/or length of the column may be modified, provided that the ratio of the column length, L, to the particle size, D, dp, remains constant or in the range between -25 to +50% of that prescribed L to DP ratio. And that's the same for both isocratic and gradient methods, although you do have some flexibility for other L to DP ratios. And that's what I have listed here with the asterisk. For isocratic, you can be within minus 25 to plus 50% of the plates relative to the prescribed column. And then for gradient methods, you can be minus 25 to plus 50% of the retention time to the peak width at half height squared relative to the prescribed column. There are changes allowed to the internal diameter for both types of methods, and the flow rate has to be scaled according to the column diameter and particle size. Continuing along with the changes, in terms of detector wavelength, there are no changes allowed. The mobile phase composition for isocratic methods, the amount of the minor component of the mobile phase can be adjusted by plus or minus 30% relative. However, the change in any component can exceed plus or minus 10% absolute. In terms of the gradient time, it needs to be adjusted according to this particular equation. And pH for isocratic methods can be changed by plus or minus 0.2 pH units unless otherwise prescribed by the method. The buffer can be changed by plus or minus 10%. That's the same for isocratic and gradient. The injection volume can be scaled. That's the same for both isocratic and gradient. And for column temperature, that can be changed by plus or minus 10 degrees for isocratic methods and plus or minus 5 degrees for gradient methods. So there are some method translators that are available for free to help you make these particular method changes. This first one is a downloadable Excel file from the University of Geneva. And then the second one is a web-based translator from ACD Labs. So now let's look at the benefits of converting to methods that use SPP columns. Just to begin, we need to look at the basic Van Deemter equation, and this is really how SPP benefits separations in terms of speed and efficiency. So here we have the plate height in microns on the y-axis versus mobile phase velocity in millimeters per second on the x-axis. And working our way down from the green trace, which is a 5 micron FPP particle, you can see that the curve is steep as you go to higher flow rates and not very low, which means you're not seeing very high plates and the plates drop off as you go to higher flow rates. If you move to a 3.5 micron FPP particle, the story is a little bit better, but not quite as good as what you see with jumping down to the 2.7 micron fused core particle. We have the lowest plate heights here, which mean the highest efficiencies, and that's even doing better than the 1.8 micron FPP trace in the black triangles. So the reason for this is in particular due to the eddy diffusion term, the A term, which is dependent upon the particle size and how well the column bed is packed. So for superficially porous particles, the bed is packed much more efficiently, and that leads to 30 to 40% smaller A terms. In terms of the longitudinal diffusion term, this is 25 to 30% smaller, and that's how flat the curve is. And then the C term, as you go to those higher linear velocities, that really helps you run faster flow rates without compromising efficiency. So to put this into action, here I'm showing increased speed and reduced mobile phase consumption. On the top here is a FPP polar embedded amide column in 4.6 by 250 millimeter dimension and 5 micron particle size. This is run at 1.5 mils per minute using a gradient from 30 to 60% B in 15 minutes. And what we've done is we've sped this up to use a halo RPM column with 2.1 by 100 millimeter dimension and 2 micron particle size, running at a half mil per minute. And we've scaled the gradient to be 3.75 minutes. So our SPP method is 4 times faster, and it's using 12 times less solvent. And you can see we're getting even better resolution between the first 2 components, the homovanillic acid and the caffeic acid. We also see increased efficiency demonstrated here using fat-soluble vitamins. So in terms of the halo column here is in blue on the top, and you can see we're getting much better resolution for peaks 3 and 4, which are vitamins D2 and D3. We get 1.62 for the resolution of that particular pair compared to only 0.87 on the fully porous particle C30 3 micron particle column. So now let's talk about understanding the impact and benefits of using a smaller ID analytical columns. I do have some words of caution for moving to smaller particle sizes and smaller column IDs. Those particular characteristics are more susceptible to extra column band broadening. And what I mean by that, everything here in the dashed black line is contributing to extra column or the total dispersion of the system. This sigma v squared total is all the dispersion, and that consists of the pre-column tubing and the sample injector, which is highlighted here in yellow, and the post-column tubing, which is highlighted here in red, and the going into the detector or the mass spectrometer. So anything outside of the column would contribute to not seeing the true efficiency of your analytical column, because it would be obscured by broadening that happens either before or after the column. We do have recommendations for ways to reduce extra column band broadening. The first way is to use the shortest and smallest ID connecting tubing between the instrument components. And we recommend the Marvel Exact connectors from IDEX, which I have a picture of them here. The other way you can reduce extra column band broadening is to use a smaller volume detector flow cell. We recommend using smaller than 2.5 microliters. You can also increase the data acquisition rate. Our recommendation is greater than or equal to 20 hertz. You can also decrease the injection volume, and this is more critical for isocratic than gradient separations. So here's an example showing extra column band broadening impact on resolution and efficiency. Our extra column volume here is 64 microliters, and we use a really large flow cell at 12 microliters. So you can see that we're not getting baseline resolution of these 3 peaks here in the middle, and the plates for the last peak are only 18,300. By reducing the extra column volume to 16 microliters and using a smaller 1 microliter flow cell, we're able to get baseline resolution of those 3 particular peaks, and we've increased the plates of the last peak by an average of 50% just by reducing the excess volume in the system. And this particular example was run on a 2 micron halo 3 by 150 millimeter column. There is a way to estimate extra column dispersion. There was a really nice series of articles in LCGC North America from Dwight Stoll Thomas Lahr and Ken Brockhoven, and they had the link to their dispersion calculator here. So what you can do is put in all of your connecting tubing volumes and injection volume and your particle size and column dimensions. And what it will do is it'll actually calculate the dispersion for your system. So on the top here, we have our standard plumbing, and this is using a 1.5 by 150 millimeter halo column. And you can see the height of the last peak is only 66 milliAU, and the width is 0.046 minutes. And I know this is a little bit tough to see, but the gray area here, this is all coming from the detector. So the anything, and what you really want to do is maximize the yellow portion of this particular graphic to show that you're getting the true efficiency of the column. So by optimizing the system, we're able to increase that yellow portion of the pie chart, and our height goes up to 150 milliAU, and the peak width reduces to 0.037. And you can see that the gray dispersion from the detector and from post-column tubing both have been reduced. So the strategy for modernizing methods that we recommend, of course, you have to keep the same USP classification. So if it's a C18 column, you have to use a C18 phase. Next, you want to calculate the minus 25 to plus 50% of the L to DP ratio for the original column. And then if the current method uses a fully porous particle column, you'd want to use a smaller particle size halo column in smaller ID and shorter column dimension. If the current method uses a SPP column, you can either use a smaller size halo column, or a similar size halo column, or move to a smaller particle, smaller ID, and shorter column dimension. So now let's look at some isocratic case studies. In terms of what changes are possible, we have, starting out with a 5 micron 4.6 by 150 millimeter column that gives us an L to DP of 30,000. So for minus 25 to 50%, that L to DP can be anywhere from 22,500 to 45,000. And what we did in the first transition here was to move to a 5 micron halo column in the same 4.6 by 150 dimension. So our criteria of L to DP is met, but what we're seeing is 30% higher plates just by changing from a FPP 5 micron to the halo 5 micron column. Then if you change from that 5 micron FPP column to a 2.7 micron halo column, we're keeping the same 4.6 millimeter ID, but now we've gone to 100 millimeter length column. The L to DP is 37,037, so the criteria is still met, and we're seeing now 57% higher plates. And that's because of the smaller particle size. And then finally, changing from a 5 micron FPP column to a 2 micron halo column in both smaller ID and shorter length, we're still meeting that L to DP criteria, but the runtime is 3 times faster, and we're looking at 41% higher plates. So these are just some of the examples of what sorts of changes would be possible. Here's an example looking at increased speed without loss of resolution. This top chromatogram is using a FPP C18 column in 4.6 by 250 millimeter dimension and 5 micron particle size. The extra column volume is approximately 35 microliters. It's using a 14 microliter flow cell and the standard length and ID tubing. So in terms of the L to DP ratio, it can be anywhere from 37,500 to 77,500. And for plates, it can be anywhere from 19,425 to 38,850. So moving to a Halo C18 column in 4.6 by 100 millimeter dimension, 2.7 micron particle size, we're able to run 6 times faster. And if you look here, we're just barely not meeting the L to DP criteria at 37,037, but we are meeting it for plates, which is 24,500. So this just shows you some of the flexibility that the guidance has enabled for SPP particle columns. Here's an example using the USP monograph for estradiol. We took a Halo 90 angstrom C18 column in 2.7 micron particle size and 1.5 by 100 millimeter dimension. And going to the smaller 1.5 millimeter ID, what we're able to do is really save a lot of solvent by running at much lower flow rates. So comparing the original method, which is run on a 3.9 by 300 millimeter column at 1 mil a minute for a total of 8 minutes, gives you 8 mils of volume. This is compared to the modified method on the 1.5 by 100 millimeter column, run at 0.2 mils per minute for 1.5 minutes, gives you a volume of 0.3. What that does is it gives you 96% solvent savings, and you can see here we're clearly in the range of that L to DP ratio at 37,037. Now let's take a look at some gradient case studies. There is, while you're making these changes, you do have to take notice, though. The adjustment of conditions with gradient elution in HPLC is more critical than with isocratic HPLC elution, since it could shift some peaks to a different step of the gradient, potentially causing partial or complete co-elution of adjacent peaks or peak inversion, and thus leading to incorrect assignment of peaks and to the masking of peaks or shifts such that elution occurs beyond the prescribed elution time. So this is just saying be cautious when you're making the changes. And then for some parameters, the adjustments are explicitly defined in the monograph to ensure system suitability. So here we have the USP monograph for cobamamide, and this cobamamide, our labeled peak, is also known as adenosylcobalamin, and it's one of the biologically active forms of vitamin B12. The original monograph column is a 4.6 by 100 and 2.6 micron particle size, so our L to DP can be anywhere from 28,846 to 57,693. And in this particular case, we just swapped in our 2.7 micron halo column and used the same conditions. So we're meeting the L to DP ratio with 37,037, and the system suitability requirements, the column efficiency has to be no less than 22,000 plates, and the tailing factor has to be no more than 2. And for both the monograph column and the halo column, both pass these criteria. So this example is really meant to show if you perhaps couldn't get the original monograph column, you could easily substitute a halo column and still meet the system suitability requirements. Here we're showing the system suitability. So the peak identities, an elution order is identical on both columns, both the original monograph column shown on the top and the halo column here shown on the bottom. Now let's take a look at how we modified the original method. So I have the equation here for adjusting the gradient times. The flow rate of the original column was 1.2 milliliters per minute. And if you scale that to a 2:1 by 75, which is what we moved the method to, the same linear velocity would be 0.25 milliliters per minute, but we're able to increase the flow rate because it's a superficially porous particle to 0.4. So this is an advantage that you have with SPP particles where you can run them at higher flow rates. And all you have to do is go through the calculations in order to generate the new gradient profile. And we've increased the equilibration time by 4 minutes for 20 column volumes for a total runtime of 25.5 minutes. And we've reduced the injection volume to 0.8 microliters from 5 microliters using this equation here. So here are the results of the modified method. You can see we're still meeting the L to DP ratio at 37,500, but now our total runtime is 1.8 times faster. And this is all due to switching to a 2 micron particle size halo column in 2.1 by 75 millimeter dimension. So we have 54 milliliters per run for the original monograph method compared to only 10 milliliters per run, which is using 5.4 times less solvent, which is really important for those labs looking to be greener and kind of improve the sustainability of their methods. Again, in terms of the system suitability, you can see that the elution order is identical on both the original monograph column and on the halo column. And for those wondering about the difference between a 2.6 micron SPP column versus a halo 2.7 micron particle size column, we have the particle size distributions of those two different particles, and you can see there's really no significant difference in the particle size, and we're seeing slightly better standard deviation for the halo column here on the right-hand side in the blue trace. So next I have the USP monograph for itraconazole, and itraconazole is an antifungal medication. The original monograph column calls for an FPP C18 column in 3 micron particle size and 4.6 by 100 millimeter dimension. And that gives you an L to DP ratio range of 25,000 to 50,000. So moving that to just the smaller particle size halo column, you can see that we're able to meet the system suitability requirements of tailing factor no more than 2 and the RSD no more than 2%. So the results look nearly identical on the original monograph column compared to the halo column. Now moving this, as we had done similarly for the cobamamide method, we've now moved it to a 2 micron halo column in 2.1 by 50 millimeter dimension. And we're now at 25,000 for the L to DP ratio, so we're still meeting that criteria, but now our total runtime is more than 3 times faster with the halo column. And we're since we're running at a faster flow rate with smaller particle size, the back pressure does increase to 402 bar, which is still well within the range of HPLC systems. But then in terms of sustainability and reduction of solvent, for 10 injections on the original method, you're using 300 milliliters compared to only 30 milliliters for the modified method, which is a 10 times reduction in the mobile phase used. And also thinking about waste disposal, that would be less waste that needs to be disposed of at the end of the experiment. We also have the USP monograph for the itraconazole system suitability. So on the top here is the original column, and the bottom is that 2 micron 2.1 by 50 halo C18 column. And you can see the original separation of the system suitability is exactly what is prescribed, and their system suitability is to look at the peak to value ratio. We're meeting that by 2 times the minimum on the halo column, even though our total runtime is more than 3 times faster, and in this case, the solvent is reduced by 11 times. We also have looked at a modified USP method for acetaminophen. In this case, the L to DP ratio can be in the range of 37,500 to 75,000. So we used a 2.7 micron column and 150 millimeter dimension for an L to DP of 55,556. So we've modernized this method using a smaller particle size, smaller ID, and shorter length column, and that's giving us 3 times faster separation than the original monograph method. And for my last example here, we have modified the USP method for rivaroxaban. Rivaroxaban is the active ingredient in Xarelto, which is medicine used to treat blood clots. And you can see the original runtime is 45 minutes on an FPP C18 column in 3 by 150 millimeter dimension. Our L to DP can be anywhere in the range from 32,143 to 64,286. And for our halo column, we chose a 2.1 by 100 millimeter, 2.7 micron column. So that gives you an L to DP of 37,037. So you can see our peak 5 is coming out right around 15 minutes on the halo column as compared to around 27 minutes on the original monograph column. And the halo column is using 1.7 times, or is 1.7 times faster and uses 3.3 times less mobile phase. Now look what happens when we switch from the 2.1 by 100 millimeter column to the 1.5 by 100 millimeter column. The method conditions are the same, except now we've cut the flow rate in half to 0.25 milliliters per minute. And you can see the retention time, the time savings is the same, but in this case, now our mobile phase savings is doubled because we're using half of the flow rate. So that gives us 6.7 times less mobile phase used per injection. And then finally, moving the method to a 2 micron, 2.1 by 50 millimeter column, you can see we're not beating that L to DP ratio of a minimum of 32,000. We're actually at 25,000. But the nice thing about the USP guidance is that you do have the option to look at the ratio of the retention time to the peak width at 50% squared. And for these particular results, it is within minus 25 to plus 50% relative to the prescribed column. So the halo column now is 3 times faster and uses 6 times less mobile phase. So in terms of modifying methods, you can really have a lot of different options depending on what your goals are in terms of speed and solvent reduction. So then in summary, the halo columns are well suited for USP method improvements. Making an assessment whether to modernize a USP method should be based on the monograph column availability and the goals for time and solvent savings. Following the new USP guidelines for gradient method modernization enables both FPP and SPP methods to be improved for speed and mobile phase savings using the Halo fused core column technology without the need for revalidation. And for those looking to improve their sustainability, the Halo 1.5 millimeter ID columns are a great option for those with low dispersion UHPLC systems. So I'd like to thank the team at Advanced Materials Technology, including Peter Pellegrinelli, Connor McHale, Dr. Taylor Harmon, Ben Liebert, William Miles, Dr. Chuping Liu, Dan Messick, Melissa Ash, and Stephanie Rosenberg. And with that, I'd be happy to answer any questions you might have. And I'll turn it back to you, Bob.
All right. Thank you so much, Stephanie, for that informative presentation. Just a quick reminder, before we get started on the question and answer session, I would like to remind our audience how to submit questions. You can submit your questions by typing them in the Q&A box, which can be found directly below the video player. So if we're good to go, Stephanie, our first question of the day. I have methods with 2.6 micron and 1.7 micron particle sizes. So can I move these methods to 2.7 micron and 2 micron particle sizes without revalidation?
Yes, as long as your system suitability is met and verification of the method has been done. So that's, that would be really easy to do, just to move those over to halo particle column sizes.
Excellent. And just following up here, the USP method we are using now uses older columns with larger particle sizes and large volumes like 4.6 by 250 millimeter. We want to speed up our methods, use less solvents, and also move to columns which are not close to being discontinued. Where do you recommend we start with modernization? I know that was a mouthful.
Oh, sure. Yeah, so there are a couple of things you want to consider when you're thinking about speeding up your methods. The first thing would be, what is your HPLC or UHPLC system pressure capability? Because if you can go to really small particle sizes and really small column IDs, then that would be really ideal for saving solvent and for the speed savings. So in general, I'd recommend starting out with a Halo 2.7 micron column, perhaps in either 4.6 or 2.1 millimeter ID by 100 millimeter length. And that really depends on your system configuration and what options you have available to you. But we are happy to help answer questions like this from customers.
Fantastic. Great info there. Next question from the audience. If I move a method which uses fully porous packings to superficially porous packings, can I just change the column or do adjustments need to be made?
So it's likely that the flow rate could be increased when you move to a superficially porous particle column. And it's also possible that the injection volume could need to be reduced. So we actually have a method conversion guidebook on our website, halocolumns.com, that goes through the steps of switching a method from an FPP to an SPP column.
Excellent. And next question here. If the audience asks, if the L to DP ratio has not been met, but the plates have been met, does this mean you can run this column method without revalidation?
Yes, that's correct. So the really nice part about the USP guidance is that you have the option of either meeting the criteria for that L to DP ratio or for the plates in terms of isocratic methods, or the ratio of the retention time to the peak width squared for gradient methods. So you wouldn't have to revalidate, you just have to verify.
Well, that perfectly leads into my next question here, just circling back on revalidation and verification. So what constitutes a revalidation versus a verification?
Sure. So in terms of a revalidation, that would be where you actually changed your stationary phase, say from C18 to C8. That would that would need revalidation, but a verification would just be needed if you went through all the criteria that the USP allows in terms of their guidance. In that case, you wouldn't have to revalidate. But the best thing to do is really go to your regulatory group in your company to make sure that you're operating where you should be.
Great. Thank you for that explanation there. This might be our last question of the day. Are there any issues with upgrading to a UHPLC system and still being in compliance with these modernization allowances?
No, I would say there really wouldn't be any issues as long as you're following the USP guidance and not changing anything drastic like stationary phase.
Sounds great. Well, thank you, Stephanie. Thank you so much for this Q&A session. And with that, we will wrap up. I want to thank the audience for attending and for participating in today's event. I'd also like to thank our sponsor, Advanced Materials Technology, for making today's webcast possible. We would like to ask everyone in the audience to please participate in a brief survey. This survey will appear on your screen after today's presentation has ended. You'll also receive an email alert alerting you when this webcast will be available for replay. We invite you to forward that announcement to your colleagues who may have missed today's live event. We hope to see you all next time. Take care, everybody.